So basically, we were discussing uh, yesterday what the sensors in on board the satellites they measure. So in plain terms, you can say that the sensors they measure certain energy which are either reflected or emitted or scattered either from the atmosphere or from various objects on the surface of the earth. In the whole process, the sun is used as the primary source of energy. It means for this kind of remote sensing, we have to rely entirely on the incoming radiation from the sun. Uh, Further, we learned that when the sun is emitting radiation or energy, it radiates energy and not only in one particular wavelength but in a range of various wavelengths. So in scientific terms, this is known as electromagnetic spectrum or EMS. So there are various wavelengths and accordingly uh, these are categorized into different names. For example, when the wavelength is extremely small, these are known as the gamma rays. By the way, the gamma rays they cannot travel too far, and from the sun they cannot reach us. So after that, if the wavelength is slightly bigger, we name it as the X-rays. Then X-rays also they cannot travel too far, and they cannot penetrate the atmosphere and reach us. After that, if you further increase the wavelength, we reach the ultraviolet rays, and ultraviolet rays also normally cannot penetrate the atmosphere due to their shorter wavelength. But nowadays, due to climate change, there is a new phenomenon that is happening. The ozone layer, which normally protects the ultraviolet rays from reaching us, is getting thinner and thinner. So we do not have a protective layer of ozone in the atmosphere. And more ultraviolet rays now are reaching us due to this effect of a depleting ozone layer. After that, normally the visible range comes if you increase the wavelength a little more. The visible range of wavelength starts from 400 up to 700 nanometer. Nanometer means 1 nanometer means 10 to the power minus 9 meter, or 1 divided by 1 followed by 9 zeros. Okay, so you can imagine the physical distance, how extremely small these wavelengths are. Within the visible range, towards the shorter wavelength, that means towards the 400 nanometer range, the colors are normally violet and blues. And within the visible range itself, towards the 500 nanometer range, we start to see the colors in green. Then if you further increase the wavelength within the visible range towards the 600 plus or 700 nanometer range, the colors of red and reddish tints they try to show up. So that means whatever color that we see, or in technical terms or in scientific way, when our sensors in our eyes they sense a particular color, it is associated with a particular wavelength. If it is red, probably it is towards 700 nanometer. If it is blue, it is towards 400 nanometer. If it is in green or any green color that you see in and around, the wavelength will be around 500 plus minus that range nanometer. Okay, so that is the story of the visible light. But the entire electromagnetic spectrum even extends beyond the visible spectrum. So when we further increase the visible range and then cross a little bit bigger in terms of the wavelength, we enter a range known as infrared. Okay, so normally infrared we do not see because our eyes cannot see infrared color. Remember, when you have the remote control, like this one, remote control, when you try to control some appliances not directly getting in contact, it uses infrared radiation. You do not normally see this particular wavelength. It may be a remote control of your TV or remote control of your car or maybe the AC. Okay, so remote infrared is slightly bigger than the visible range. Within the infrared also, it is again subdivided into near infrared, mid-wave infrared, and short-wave infrareds, and far infrared. So you don't have to really go into these things, but remember, infrared is slightly bigger in terms of the wavelength compared to light. So further, if you extend the wavelength, we see or we normally encounter the microwave radiation. So microwave radiations, they have a physical distance starting from centimeters up to a few tens of centimeters. Okay? So microwave, you often hear when you have a microwave cooker or any other microwave appliances, they normally use the wavelength in this range. Then after microwave, we enter the radio waves, which are extremely longer in terms of the wavelengths. So physical distance may be the size of a football field. So what is the advantage or what is the attribute if the wavelength becomes longer? When the wavelength is longer, the wave can travel farther. Remember that. So that is why in order to communicate with extraterrestrial objects which the scientists are looking into the universe, they normally use radio waves because the radio waves, even if they travel farther and farther distances, they do not lose the energy. And then you can reciprocate using radio waves. But in case of shorter wavelengths, for example, gamma rays or X-rays, they can travel far due to the shorter wavelengths. Okay? So remote sensing normally uses three different ranges of this electromagnetic spectrum. One is the visible light, that is known as optical remote sensing. I would strongly suggest you write in your notebook, okay, whatever things I'm saying. So if you are using visible light or if you are using a range of wavelengths starting from 400 to 700 nanometer for remote sensing investigations, this is known as optical remote sensing. Okay? If you are using a wavelength range slightly bigger than that and it falls in the infrared category, this is known as infrared remote sensing. And then if someone is using microwave radars, RADAR, radar, for remote sensing appliances or applications, it is known as microwave remote sensing. So there's different kinds or three different kinds of remote sensing. they do have their own advantages and disadvantages. Okay? We will look into those in a later class. Okay. So far, this is what I wanted to say in this slide. Then let us go to the next slide. Can you see this? This is a very important slide whenever you want to study the subject of remote sensing. So this tries to elaborate the concept of reflectance. What is reflectance? Whenever you try to read a paper, or if you are talking to someone in terms of remote sensing science, you will hear the word known as reflectance. Okay, so what is reflectance? So reflectance, actually this is a ratio of the amount of light that is reflected from a particular surface to the total amount of light that falls on the surface. Okay, so you can call it light or you can call it energy, because as you know, light has got dual characteristics. It can be assumed to be having a wave format, as well as it also has energy associated with it. The unit of energy is known as photon. So reflectance is the ratio of the amount of light that is being reflected from a particular surface to the total amount of light that is incident or falls on that surface. For example, if I ask you what is the reflectance of this cover of my mobile phone, so then I will consider one square, you see, one square unit of the surface area. Okay, that may be 1 centimeter length, 1 centimeter wide. That is the size. So on that particular size or area, I will look into how much of an energy actually is falling in terms of light energy. And then, because of the property of this ladder or the object, it is absorbing a certain amount of energy or light, and then at the same time it is reflecting back a certain amount of energy or light. So when I ask someone what is the reflectance of this mobile cover, then he has to answer, or she has to answer that, okay, this much of an energy is being reflected from this particular mobile cover, while the total amount of energy that is incident on this mobile cover is this much. So you divide this reflected part by the total part, you will get a number or a figure, which is normally dimensionless, because the units will cancel each other. So reflectance is ultimately the ratio. Okay, so you can talk in terms of ratio, or if you multiply it with 100, you will get the percentage. So why this is important? Because every particular object that you can imagine, they do have a unique reflectance pattern or unique reflectance percentage, depending on the property of the object. So the amount of reflectance I will expect from this particular object will be different than the amount of reflectance normally I will expect from this particular object. Okay? In plain term, if the object is able to absorb most of the incident energy, for example, this particular object, and reflect very few. What color do we see? Hmm? Do you have this idea? Normally, if you see something in black color, it means most of the incident energy is being absorbed by the particular material. Very few is being reflected. On the other hand, if you see something in white color, normally call it color, it means most of the energy that is incident on this particular object is being reflected back. Or the other way of saying it is, this object has got a higher reflectance than this object. Understood? Yes or no? Any doubts? Are you there?
Yes, sir.
Yes, very good. So, any doubts? Any doubt? Anything you want to ask? Because the questions
Not
will
yet,
be,
sir.
you will be able to answer the questions once you only understand the concept. Okay, for example, this one, the clothes that I'm wearing today, you see it in the red color or crimson color. Why? Because of the property of the object or the material with which the cloth is being manufactured. It is such that whatever amount of energy or whatever wavelength is incident on this particular material, most of the wavelength is being absorbed except the wavelength which falls into a category of red color. It means this material is absorbing most of the energy or wave that is coming from the sun because of the property or the chemical property of the object. It is absorbing a certain amount of wavelength or energy. At the same time, it is reflecting back. So it is appearing red because the reflected energy coming from this particular object falls in the category of red color. That means within or near 500 nanometer range. That is why it appears to be red. If most of the energy is being absorbed, nothing is reflected back, it will look like this in black color, mostly in black. If almost all the energy or all the wavelengths are being reflected back, it will appear in a whitish color. So whatever color that you see, remember, this particular object is reflecting the energy corresponding to that wavelength. Okay? So try to think that way. If you're seeing something in green color, particularly the leaves of the trees or the paddy field, it means because of the chlorophyll which are present in a leaf, it is absorbing all the energy that is coming from the sun except the green wavelength which it is reflecting back. That is why it appears to be green. Okay? So, as I said, every object you can imagine, it has their unique reflectance depending on the chemical and the molecular property of the object. And this is the key to understanding remote sensing. later on you see in the slide. Yes, look at this. So here you see a graph on the left side of the screen. Okay? So on the y-axis, it is the reflectance which is being plotted. Reflectance means, as I said in the previous slide, this is the percentage or the amount of energy that is being reflected from a particular object or a particular surface. And on the x-axis, you are plotting the corresponding wavelength which is contributing to that particular reflectance. Okay? Now, let us consider various kinds of trees or leaves. So this example, we are considering three different kinds of trees. Someone from botany, maybe it is easy for you to understand these different kinds of trees. Birch, pine, and fir. Of course, these are not familiar with our environment. This example holds good for any kind of trees. Okay. Uh, Take an example of the first kind of tree or birch. So when you see that near, look at the x-axis, zero point 0.4 micrometer. That means around 400 nanometer. How much is the percentage of reflectance? It's less than 10. That means when you consider the blue wave or blue range, it is mostly absorbed by birch trees. When you go a little farther, that means when you are increasing the wavelength slightly, then you will notice that the percentage of reflectance is slightly getting increased. That means towards the greener spectrum, you see a higher amount of reflectance. That is why normally the leaves of the trees, they often appear to be green. So the moment you enter the green range around 500 to 600, you will see the maximum peak around 20. So that is why most of the leaves you see in green color. And then you further increase the wavelength, the reflectance goes down, drops. Reflectance drops means there is not the dominant wavelength. So whatever is the dominant wavelength, you see the color in that particular range. So in this case, you see this is the spectrum, this green line for the bird's leaf. It in the blue range it is less. If you increase or keep on going, it is also increasing, and in the green range it is achieving a peak, and then farther beyond, when you are entering the near infrared, after green, when you are entering the red, it drops. That is why you do not get to see normally the leaves in red color. So in case of a leaf of a tree, which is the dominant range? The green one. Why? 0.5 to 0.6, this is the green range. Look at this slide. Look at these numbers. On the right hand side, this is 400. On the left hand side, this is 700. In between, this is 500. What color is this? This is green. It means normally if you see anything in green color, this is likely to be in and around 500 nanometer. Same thing happens. So you see, this is 500 nanometer. 0.5 micrometer means 500 nanometer. 500 to 600 nanometer, this is the dominant range. That is why you see all the leaves in green color. And then towards the red, it drops. And an interesting phenomenon we observe is that if you go farther, if you keep on increasing the wavelength, there is a sharp increase in the reflectance. See, from 700 plus to 800 nanometer range, we have the maximum reflectance that is coming from a particular leaf of a tree. But unfortunately, our eyes have the limitation that we do not see what is happening after 700 nanometer range because our sensors are not designed to capture this information. Unlike an infrared camera. So we can see only from 400 from here up to 700. So we can see only this part of the picture. We do not see these peaks. Why? Because these are happening in the near infrared range and we do not see what near infrared responses are normally with our naked eyes. So that is why our eyes, when we recognize something of a response that is coming from a leaf of a tree, we have the maximum response in this range, around 550. And 550 corresponds to the green range. That is why the leaves of the trees, we see it only in green color. But again, when you look minutely into these three different kinds of graphs, you will see that depending on the kind of trees, there is a slight variation in the response of the reflectance. So that helps to distinguish one tree from the other. Okay? Though they fall within the bigger category of trees, due to this minor change in their reflectance pattern, we or someone can distinguish if this is a birch tree or this is a pine tree or this is a palm tree or it may be any other tree. And this is the beauty of the subject of remote sensing. That means this response you are getting from about 700 to 1000 kilometer from the surface of the earth. Imagine from 700 kilometers away, you can tell if this is a palm tree, this is a birch tree, or this is a pine tree, or this is any other tree, or if it is tree at all or not. Right? This is the power of the subject. This is not only used to classify trees, this can be used to classify different minerals, stones. For example, if we are looking into a kind of stone which is having a name of chlorite, it will have a response or reflectance pattern like this. If you get a response or a reflectance pattern that may be coming from a particular other kind of stone that follows this, you can be sure that this is a limestone. Or if it is having a particular signature like this, it may be a muscovite or a dolomite. See, the wavelength that you are engaged in this investigation are the same. Okay? So, depending on what kind of a reflectance you receive at different wavelengths, we can tell with almost certainty that this object is different from that particular object, or what that object really is. And that too you can tell from a distance of 700 kilometers away. That gives you a very, very powerful tool in your hand. Okay? Again, look at this light. This is on the right hand upper corner. You see that these are different kinds of land use or land cover patterns which we often see normally. What are these? So if you just walk in and around your place, you may come to see there is a pool of clear water, or there may be a river which is flowing near you, which is turbid. That means it is carrying a lot of sediments. Or there may be an area which is covered with the trees, but there may be an area which is devoid of trees, or simply bare soil, or a fallow land. Now come back to the kind of responses that you may get from these particular land covers. Look at this graph. Same thing. If this is clean water, this one, then look at the kind of response you expect. In the 400 nanometer range, it has the maximum response around 13%. See, look at my x-axis, 0.4. Look at this blue graph. The maximum you get when the graph is touching here. That is, if it is 10, maybe this is around 12. That means 12%. The moment you increase the wavelength, 0.4 and 0.5, this reflectance drops. That means towards the greener side, you get lesser response. You further increase the wavelength towards the red, it completely vanishes or drops to the minimum. So normally what happens when you see clear water, what color do you see? What color do you see of the clear water? Yes. Come on. What color do you see when you are looking at the clear water?
Blue.
Blue. Very good. Why? Because in the blue range or blue spectrum, we have the maximum reflectance or maximum response that is coming from that particular range. And if you want to ask me why in blue it has got maximum response, so you will have to really go into the deeper chemistry. That is actually beyond the scope of analysis for us right now. This level. Why? In the blue range, it has the maximum response. What property of the clear water actually influences that? Okay, that is the part or job of the chemical scientist to investigate. Now look at this turbid water. Turbid water means clear water when it is mixed with a lot of sand or soil or any other debris. We call it turbid water. Normally, when there is floods that happens, a flood occurring after a lot of rainfall, you do not see clear water inundating all the houses or lands. Mostly it is the turbid water. That means this water is mixed up with sand or soil. So look at the response of the turbid water. Which one is the turbid water? This color. Okay. So in the turbid water, in the blue range or in the blue wave range, we have a reflectance, for example, of around 15%, between 10 and 20. Then towards the greener side, this keeps on increasing. And in the red zone, it reaches a maximum. So it's a mixture of green and red, where you expect a higher reflectance. Then it drops. In the near infrared zone, we do not see a lot of response coming from either clear water or from turbid water. So the reason why the turbid water appears to be brownish or not blue is that in the brown or the reddish regions you expect higher reflectance. Okay? Similarly for bare soil means soil which do not have pastures or grass or leaves. Normally, often this is in reddish or dark brownish colors. So in the blue range, around 400 nanometers, we have a lesser reflectance. Towards the green, it keeps on increasing. On the red, you achieve a maximum, and then if you cross this region, it keeps on increasing. But unfortunately, we cannot see beyond 7 or zero point 0.7. So this story, the graph, we do not see with our naked eye. But remote sensing satellite sensors, if it is built to capture this information, they can tell you this unfinished part of the story. Okay? So when scientists or engineers they design these sensors may be designed in the blue range or they may be designed to capture information that is coming in the blue range or in the green range or either in red range or near infrared, whatever range you want, depending on the kind of application. Okay? Now, come back to visitation. In a visitation, we observe a very unique and typical signature. Look at this green graph. In the blue range, this is around 8 or 8%. Then it drops, and then in the green range, it becomes maximum around 12 or maybe 13. Okay? And then in the red, it drops. So after red, we don't see, but normally in the near infrared, it reaches this maximum value of around 50%. That means most of this energy which is being incident on a leaf, maximum energy is reflected back in the near infrared spectrum. If you somehow can capture this information, you can see all the leaves to be exhibiting an entirely different kind of story. We normally cannot see that with our naked eye, but at least we can build sensors which are or which can possibly capture this information. Okay? So, as I said, why this reflectance concept is so important? Every object on the art, they have their unique way of reflecting or reflectance. This is known as their signature or reflectance signature. Like my signature is very unique to me, the objects they also exhibit this uniqueness in terms of reflectance. So by knowing this signature, you can tell if this is vegetation, this is clean water, this is bare soil, or this is turbid water, and most importantly, within vegetation also, if this is a birch tree, or if this is a pine tree, or if this is a fir tree, or if you are talking about different kinds of stones, if this is chlorite or limestone, or dolomite, muscovite, okay. So that's why I say remote sensing, this is a tool. This is a science, this is an art, this is a subject itself. At the same time, you can use it as a tool. For someone who is going to study botany, maybe he will be interested in this part, left hand side of the screen. Someone who is a geologist, he will be interested in the right hand side of the screen. He will be interested to know what kind of stones are there, what kind of minerals are there. So his interest will be towards this side. If I am studying botany, I will be more interested towards the left side. If this is what kind of tree is this? Or if I am studying disaster management,